Title of this talk is Robust Stream Processing with Apache Flink. Anyone in the room know anything about Apache Flink? Some hands? A little bit? Okay. Quick background on me. I'm the Director of Applications Engineering at Data Artisans. Data Artisans is the company formed by the guys who originally created Flink. And now we exist to continue to push the technology further and to also support people in production settings. There is a release of Apache Flink from Data Artisans that we do support directly. My background is in streaming computation. I worked various other things as well, but I worked on the streaming compute team at Twitter for a bit. I also worked at a company called GNIP, which is basically a big stream processing engine, big stream processing and filtering engine. There's another guy in the audience right here that was also part of the same group. And before that, I worked on video stream processing. So I've kind of been in the stream processing area for quite a while. All right, the overview today is we're going to start with what is Apache Flink for the people that don't know anything about it. Then we're going to talk about basically what I call the world's quickest introduction to stream processing. And then we're going to focus primarily on stateful stream processing. And I'm going to describe what that is and why it's different, and also why it's more interesting. And then we'll talk about windowed computation over streams. And then the real stuff, the real meat of the talk is going to be about robustness in stream processing. So we're going to talk about robust time handling. We're going to talk about event time versus processing time, which is something that's talked about a lot in the stream processing world. I'm going to actually show you what the difference between these two things is and why it matters. And we're going to talk about failure handling. So these are distributed systems. Flink is no exception. It's a distributed stream processing system. So things can and do fail. So I'm going to show what happens in the case of failures and how Flink makes sure your computation is still robust. We're going to talk about downtime handling. Sometimes you have to shut things down. Sometimes you have to upgrade clusters, things like that. How do you do this in the face of stateful computation, right? I'll point out when we get to the slides on stateful computation why this is harder than it used to be. And we're going to talk about reprocessing. So when you have a streaming application that's running 24/7, then you decide you want to change something and you want to go and reprocess, like say the last year of data. How do you accomplish that? That's something that in the real world with production systems, this is something that happens all the time. Most systems in the past, you ended up cobbling together some sort of solution based on maybe some different code with a batch processor, and I'm going to show you how to do this the streamlined way. Okay, so what is Apache Flink? It's an open source platform for distributed stream and batch data processing. Notice I did say batch processing in there. Flink is actually a very good batch processor. That's actually what its genesis was. The project started at the Technical University of Berlin. The idea was to apply a streaming data flow engine to batch workloads, because if you pipeline the shuffles and stuff, you can actually get much higher performance. So that was the genesis of the project. So it's always been a streaming system at its core. Now people are much more interested in the streaming side, but actually Flink does do both types of workloads. This is kind of what it looks like at a high level. I need to update this a little bit, but you'll see you can deploy it a few different ways. Standalone cluster, on Yarn, Mesos is coming. It's actually in the Flink master code now. So in Flink 1.2, which is in a couple months, there'll be full Mesos support. But the next layer up is the runtime. It's just one runtime. Whether you're doing batch or stream processing, it's the same runtime. It's a distributed streaming data flow engine. That's really the core of what Flink is. On top of that, you have got a data stream API and a data set API. You can think of this as batch and streaming, or you can think of it as the data set API is when you have bounded data sets that you want to do some processing over. Data stream API is when you have infinite data sets, right? So it's just an unbounded series of events that continuously are arriving, and you want to process in a continuous model. So that's the two APIs. And then layered on top of those are a few other libraries, complex event processing. There's a table API, sort of like a relational API. There's now streaming SQL support, which isn't drawn in this diagram on the streaming side. And then the same on the batch side, there's a machine learning library, there's a graph processing engine called Jelly. And then there's also the same sort of relational API and SQL support on the batch side. Okay, so this is the intro to stream processing, the quick version. This is stream processing. You have an unbounded data set called a data stream, right? You have your code, and you want to create an unbounded data set as well. That's stream processing in a nutshell. I will mention here that batch processing is you just bound the data set, and you have the same thing, right? So batch processing is a subset of stream processing, in my view anyway. So simple version of stream processing. In this model, you can do simple things like transform, map, parse the data, and like maybe output some other format, those kinds of things, filtering, etc. So you can do some things, but it's not very interesting until you get to here. So this is stateful stream processing. This is a relatively new thing to be able to do this and do it robustly. So that's mostly what we're going to talk about today. Stateful stream processing is, same thing, an infinite unbounded data stream. Some computation you want to do. You can generate output continuously, and you can update, you can keep, update, and read state, right? So now you have, this basically is a stateless model. Imagine if like none of our computers had any memory, right? What kinds of programs we could write? That's what this is. This is a stateful model. So this actually means you have at your disposal now memory. So you can actually update data structures, you can do whatever you want in terms of processing, you can keep state, and Flink will manage all of this. This is the important part. This has to be fault tolerant. When we distribute across a bunch of machines, we have to be able to keep this state fault tolerantly. And if there are errors, we want to be able, or sorry, if there are failures, machine failures, et cetera, we want to be able to still compute exactly the same result as we would have without failures, right? So that's what stateful stream processing is about. This model you can do, basically the sky's the limit, right? You have a full computation engine here. Okay. So in the real world, we don't just do this. We actually string multiple stages of these things together. So maybe we're reading from a queue like RabbitMQ, files on HDFS, maybe we're reading from Kafka. We do some maybe filter and map on a couple different streams. We can join streams together just like a database join. We can compute windowed aggregates, all of this kind of stuff. And then in the end, maybe we're going to write to Influx, which is a time series database, or we're going to write to Cassandra, some other data store, back to HDFS, back to Kafka, et cetera. But the idea is you basically build graphs of computation. Each of these things can have and hold and keep state, and then you eventually sync the data somewhere. And then we don't just do it once or on one machine, but we distribute these graphs on lots of machines, and we use a bunch of machines at our disposal to either do very high throughput computations. I mean, say you've got millions of messages per second, so you need a bunch of machines to actually segment the work and process it. Or maybe you just have really heavy computation, either or. You have a framework that allows you to distribute this workload across a bunch of machines, but the computation should always be exactly as if it was run on a single machine. All right, so correct in the face of failures is what I really mean by that. Okay, and I just threw this in. This is based just as a data point, so you kind of get a sense of what's possible. This is a benchmark I did with Flink on a HPC cluster. I actually did this in partnership with MapR because they lent me the hardware for this. But basically 10 machines, 40 gig interconnect between all the machines, because that's usually the bottleneck with Flink is the network. Flink itself is very efficient. So on those 10 machines, I was able to read 72 million JSON messages per second, parse, and do sort of like a keyed window to aggregate, and then write the data back out. So this gives you an idea of what's possible on, this is only using 10 machines plus Flink. So it's very, very efficient. Okay. So we get to the meat of the talk here, robust stream processing with Flink. We're actually just gonna, for pretty much the rest of the talk, I'm gonna be writing some code, and I'm gonna be demonstrating various things that we've already mentioned. So hopefully it will be fun. And let's just get started. All right, can you guys see that okay? Is it readable? Let's see. Yeah? Okay. All right, so this is just the stub of a Flink program. And I'm just going to develop this code right here and run it in my IDE, and then later we'll switch to running it on a cluster. It's still going to be local just to keep it easy. It's going to be a local cluster here, but I want to show you that you can actually just get started with Flink inside IntelliJ and run jobs like very quickly. So to start, we are going to just consume some generated data, and I'm going to gloss over this a little bit just because for time purposes, but we're just going to start here. I'm just going to show you, let's look at what the data is. So I just defined a source. I'm reading some data, and I'm going to zoom in here. And then I said, hey, let's just print it to the screen, just as a test thing. So what we have is data that looks like this. It's a timestamp. It's a key that says what sensor did this come from. The idea is we're simulating like IoT sensors. We have a door sensor that says whether the door is open or closed. We have a temperature sensor that gives you the temperature. We have a pressure sensor that gives you pressure. And so this is what the data looks like. It's just one data stream. All the data is kind of intermixed from all the sensors. It's just like a big fire hose of data. So if we want to get a little bit more insight into this, we can instead, let's take that stream and write it to something like, let's write it to influx where we can actually look at it. So I just added a sync, right? So that's just a concept in Flink where you can sync the data somewhere. It could be, like, again, Kafka, et cetera, et cetera. You can write your own syncs. They're very easy to write. This, for example, is the influx sync. This is all of the code right here. Yeah, maybe it's not really, it's demo quality as opposed to production quality, but I just added support for influx for this demo. Okay. So if we do this, and we just run this program right here in our IDE, and we go and look at this, I've got influx running on my laptop, and I've got Grafana running to read from influx, right? So this just allows you to see kind of the starting point. This is the data we're starting with. We have a temperature sensor that basically looks like a square wave. We have a pressure sensor, which is a sine wave. And we have this door sensor that's just kind of a square wave. All right, so let's do something now a little bit more interesting with this. And I'm going to show you, before I write the code, what we're trying to achieve. This is a stateful function. This is, what it is, it's going to be an amplifier. It's going to be a dynamically programmable amplifier. So what we have is the data stream, this is going to be the raw data we were just looking at. It's just going to be fed into this amplifier function. And there's going to be a control stream. And on the control stream, I'm going to be able to basically type commands onto a socket connection. And it's going to say for each individual sensor, apply some amplification factor, okay? So there's going to be this little amplifier function. It's going to consume two streams, control stream, data stream. The state is going to be the current amplification factor for every key, for every sensor in the system, right? So that's what we're going to use the state for. And the output of this is going to be the same waveforms, but amplified according to whatever factor we say. So let's see how we can write something like this in Flink. And by the way, this pattern of a sort of dynamically programmable operator is extremely common and extremely useful. People use this in applications all over the place. A really good example would say like a programmable filter function where you change the filter rules at runtime in order to change what the output of the operator really would be. So we're going to build this thing in Flink. And so the way we're going to do that is we're going to read from a socket on my local machine on this port. Okay? And then we're going to take that's just going to read in strings. And then from there, we're going to parse out these things called control messages. Let's see if I can remember this. Okay. Let's call this the control stream. Oops. And then we are going to, let's see, to create this operator with two inputs, we're going to do a connect. So we're going to connect two streams together. We're going to connect the the main data stream with the control stream. Okay. And then we're going to do this operation, which is this amplifier. Whoops. And I'll show you what that function looks like. It's also quite simple. And then finally, we're going to, let's write this stuff to also to influx. Sorry. We're going to call this one amplified. Okay, let's see what this gives us. Oh, and if you're curious, this amplifier function, which is the thing I just sort of diagrammed, is really simple. Can you read it okay? It's hard for me to see it. Basically, it has two inputs. So those are the two flat map functions you see here. On one side, you get these control messages, which is what I'm going to write to the socket. And all it's going to do is basically update the state. So for some given key, I'm going to update that key, and the value is going to be the amplitude that I read from the command line. And I'm literally building state by key, and each key will have a different amplitude saved. And then this is actually processing the data. So data's streaming in, I process message at a time, and for each of those messages, I get the current state for that key, and I compute the current value times the amplitude. It's really simple, actually. That is our little amplifier function. Again, this thing. That's what we just wrote. We just wired this together, and let's see if we can just run this thing. See what we get. Let's see. Whoops. 1 second. There's some error. Let's see. Oh, sorry. In order to use keyed state, the streams actually have to be keyed. Okay, and something interesting, this gets distributed across a cluster, right? So if you have these two data streams and you key them both the same way, all the messages with the same key are guaranteed to end up on the same machine. So you're building up the sharded state across a cluster. If you key both streams the same way, it works very naturally. So, in a sense, you can think of it as we're building this big distributed sharded state store. We're building up the state. Okay? So then I can switch here to my, sorry. I need to zoom in on this stuff. So now for the temperature, I'm going to say the amplitude should be 1. For the pressure sensor, amplitude should be 2. And for the door sensor, amplitude should be 3. There we go. Does that make sense to everyone? So now we have this stateful amplifier function that for every signal, it has a different amplitude. And that's our current state. If we want to change the state again, it's just a stream. So let's stream in another change. Let's make the pressure sensor really big. Right? Okay. So that's what we have so far. We've built this. The next thing I want to do, now that we have some basic interesting data, I want to do windowing. The reason windowing is important in stream processing is because streams are infinite. So if you want to do something even basic like compute some sort of sum over the data set, you have to at some point bound it. Like in batch processing, you just take, you consume all the data, and for every key, you can generate a sum. In stream processing, there is no, it's unbounded. So you have to define windows And a window is a way to take infinite data set and say, for this part of the data set, I want to calculate some values, statistics, some aggregate, etc. So let's do some windowing next. Okay. Are there some programmers in the room for sure? I just wanted to make sure like this isn't, okay, awesome. That's what I thought at this conference. I just wanted to make sure. Okay, good. All right, so the next thing we want to do, let's call this our amplified stream so we can reference it. Oops, same thing. Let's see. Oh, whoops. Whoops. Okay, so we have this keyed stream again. And for each key, we want to compute a window individually for each key. So what I'm going to do is we're going to sum up each of those different, basically each of those different signals over some time period. So, okay, and then once we have a window, we're going to reduce the data by summing. And then we're going to write it out. Once again, we use our influx sync. We're going to call this summed sensors. Okay, so now we have kind of an interesting set of things going on. We have the raw data we're writing out to influx. We have this amplified stream we're writing out to influx. And then we have this, we're going to take that amplified stream and we're going to sum over it. And we're going to write that out to influx as well. And they each kind of have a different name. This is called a measurement. This is the measurement name in influx. But basically, let's see what that gets us. And I've already got the graphs and Grafana set up. Okay. So we're back to our zero state, right? So if we look at these amplified sensors, we haven't amplified any of them. They all start at kind of with an amplification factor of 0. So we're starting at the 0 state. We're going to get to that. Normally, you never get to go back to 0 state in stream processing because this thing has to compute state. It runs 24/7. You never see 0 state ever again, like once the thing starts. So we're going to fix that. But let's just get some data going again. Some different amplification factors. Okay. So now we're summing these things up. And if we look at, say, the pressure sensor is a sine wave. Okay? I'm going to forget about the other two for a minute. The pressure sensor in the middle is a sine wave. And we're computing a sum. The period of that sine wave is 1 second. If you look at the code there, the window I defined is also 1 second. So in theory, if I'm summing over that same second, and we're summing over a sine wave, what should the answer be? What should the sum be of a sine wave? 1 period of a sine wave. 0, yeah? Exactly. It should be exactly 0. So we look here at this middle thing where we have this summed pressure, and it's kind of 0. It's 0-ish. It's kind of hovering around 0. Does anyone have any idea what might be happening there? Like, why isn't it exactly 0? You have an idea. I can tell you have the idea there. Right. So what he just said is the window isn't exactly aligned on the cycle, right? That's exactly what's happening. The other thing that's happening is what we're doing is we're summing in processing time. We're defining a window of 1 second, and the clock we're using to define that window is just the machine clock, right? Not a good way to get accurate analytics because data actually arrives from devices in the field. Maybe it passes through Kafka, it gets backed up, it comes in bursts, all of this stuff. If you're doing this in processing time, this is going to affect your analytics. And so this is bad. The other thing is What if we're trying to replay a bunch of historical data at 100 times the speed? I don't want all of my sums to suddenly be 100 times the value, right? So this is the reality of processing time. So any stream processing systems you've used before or in the past that are doing things in processing time have all of these problems. It's not a very robust way to do things. I have a slide that makes it a little clearer for anyone just to see what's happening. This is what's happening. We have processing time and we have event time. The events actually have timestamps in the data. But we're actually just drawing windows in processing time, just like the time on some machine, right? That's how things in processing time work. So we're doing this and we're getting errors because those windows aren't right. What we really want to do is actually look at the raw data, extract a clock. This is the way I think about it. It's the best way to think about it, I think. You extract a clock from this data. And by the way, the data can be totally misordered. That's the real world. Things don't come in time order. But nonetheless, we want to extract a clock that is well behaved from the data. And actually then when we compute windows, we want to compute them correctly based on this clock. And in fact, everything we do in the stream processing system that uses time should use this clock, this nice ordered clock extracted from the data. So that's what we're going to do. All right, so luckily in Flink, this is pretty easy to do. And this is really what's called event time. Event time support is really important. So all we're going to do is say set time characteristic to event time. And then we have to do one other small thing. This control stream, you guys saw I was just typing temp 1, pressure 2, etc. It doesn't have any natural timestamps, so I have to make up some timestamps for it. And that's what I'm doing here. I'm kind of going to gloss over this, but we can talk about it maybe at the end or if there's time. Let's see. Because they need to have timestamps too. And what I'm doing is I'm just giving them the max timestamp possible. It's not really important, but it is required. For event time to work, you have to have timestamps for everything. Okay, so now when I run this guy, what we hope to see is that those sums, let's get some interesting data again. Got to amplify some stuff. We'll fix that in a minute. Okay? Now what we see is that this stuff is rock solid. Does that make sense to everyone? That's event time. So what this really means is that we're now, has nothing to do with what speed we're computing at, when the data arrives, if the data is misordered. The clock we're using for everything comes from the data itself. It's extracted from the data itself. Okay? Yeah, so it's based on a system called watermarking. And I'm going to put that, basically what a watermark is every once in a while there's something in the stream or there's a heuristic that lets you know that some level of completeness has come to pass, right? So you know based on, and what your watermarking strategy is something that it really depends a little bit on the data set. But basically every so often there's a watermark, and the watermark says, I don't expect to see data older than this again, right? And then based on that local thing for every partition, in this, again, this is a distributed system. You have this local information at every partition, and from that, Flink figures out the rest in terms of every operator in the system. It can kind of calculate what is the current time in event time. And it's extracting that from this misordered data. But you get this nice stable clock, and then you can continue, right? So that's what that is. And I like to demonstrate it this way because it's really this. Processing time equals errors. If you're doing analytics, the whole idea is robust computation over streams. If you're not doing this, you're doing it wrong. Basically, you will have errors in your analytics. And with event time, you get accuracy. It's worth mentioning maybe that this applies to most batch processing as well. A lot of people have continuous batch processes, and really your data's arriving, you're throwing it into batches based on time on HDFS or something, and then you're computing analytics over these batches. It's got all the same problems. Just you need a continuous model in order to sort all this stuff out. So, yeah, because you're really just bucketing based on arrival time. Same thing as processing time. Okay, so the next thing I want to do is show some failure handling. Let's switch to, I'm going to shut down this in IntelliJ. So far, I haven't ever had, if you were doing the same exercise along with me, you wouldn't have ever had to install Flink. This is just, you took a Maven dependency and you run your project, it all runs in IntelliJ. So it's really easy to get started. But now I'm actually going to run a little Flink cluster right here on my laptop, which I already have installed Flink, which just means I downloaded a tarball and unzipped it. But now I have a Flink cluster running. And then the other thing I have, I'm just going to build the same code right here from the command line that we've been running in IntelliJ. Okay, and then I'm going to run this job. Let's see what happens. Okay, and here, now we can look at this too. This is the Flink UI. So we submitted a job. This is our running job. This thing at the top is actually a graphical view of like what Flink does with your program. Some of this is part of the data generator that I kind of skipped because that was just our starting point. But this is, if you take the code we just wrote, this is actually the data flow Flink creates from your program. So Flink takes your code. It's you have this sort of declarative code. There's essentially like a translation or translation step. It generates a job graph. That's what we're looking at here. And this is what executes on the cluster. If you look like this, for example, this piece is our amplifier function right here with all the inputs coming into it. And then it's got this regular sync plus the windowed sync as output. But that's the whole job graph. And here's a bunch of stats about what's happening at each one of those operators. Okay, but the point we want to get to now is failure handling. So, one more time, I will do this, and then we can stop doing this because we're going to fix it. Okay, so this is a running Flink program. Now, let's just go and simulate a failure. One of the processes involved in running a Flink job is called a task manager. That's where your code runs. I'm going to find one, the one that's running our code, and I'm just going to go and like kill it, brutally kill it. That's it, gone. So the data flow is going to stop, of course, because there's no process out there to run our code. I'm going to zoom out a little bit so we can see what's happening. I just zoomed out in time. Okay, so what's happening right now is that there was this Flink job running. One of the processes involved in this died, or the machine out there in the real cluster died, and Flink wants to restart the job. If we were running on Yarn or Mesos right now, this would have already recovered, like basically almost instantaneously, provided you had a couple extra slots around. Or if you had to actually wait for a new machine, you're going to wait for Yarn for some amount of time, and then Flink's going to try to restart this thing. Right now, I'm the resource manager, so you can think of me as Yarn, and I'm going to give resources back to the cluster. Flink's just trying to restart this thing right now. Okay, so I'm just going to fire up a task manager, and it's going to rejoin the cluster, and then you're going to see resources come back online, and then the job's going to restart. Okay? The problem is, look at all that downtime, right? All of this data is missing because we were down for a while. Not only that, but we lost all of our state. There's actually a lot of state in this because we're computing Windows. All that stuff has state in flight. The data generator itself has state. But really, obviously, that amplifier function we built has state. And we've lost it all, right? This is what we want to fix. Okay, so really, this is really the crux of stateful stream processing. You know, if we had a stateless system, great. It's easy. You just start back up and everything's fine, right? But this is stateful computation. So we need to recover all of that state if we're ever down. So all I have to do, and I'm sure a lot of people want to know more about the algorithm, how this works. Maybe there's time at the end, or I'm here at the conference all day, we can talk about it, but I'm just enabling checkpointing. Flink uses an algorithm called lightweight distributed lightweight asynchronous distributed snapshots. There's a great paper about it if you want to know how this stuff works. But basically, the new thing that's been solved, in my view, is that you can introduce essentially exactly once processing with regard to all the state we're computing, with regard to what we're computing in Flink, and we can do this with almost zero latency hit and almost zero throughput hit. That's what's new in Flink, in my opinion. So that's pretty important. Nonetheless, we're going to turn that on, and we're going to recompile, and we're going to do this experiment again. I just say list the running jobs. I'm going to kill the job that was running, and we're going to submit the job again with the new code, just with that one change. Okay. Okay, and then we're going to do this process again. Now we're to the state, we're running, we have checkpointing, we have fault tolerance turned on, basically. And now, last time, we're going to do, whoops. We've got some interesting state. And this time, I'm going to do the same brutal thing. This. Okay, so same thing. I killed the task manager. Flink's looking for resources. It's waiting on me. I'm the resource manager. I'm going to decide when there's stuff to add resources, give Flink the resources it's looking for. But what we expect to see this time, what we want to see, is that we would like to see that this graph looks exactly as if it would have if we wouldn't have had any failures, right? That's what we want to see. So all of this state, it should come back up, it should continue the computation. Everything that was in flight should still be in flight, and everything should still be correct. So, run a task manager and see what happens. There you go. So that is an example of how you do stateful computation over streams and handle failures properly. All right. And this, again, this could be distributed across many machines, and this would still all work the same. Okay. So, yeah. Downtime handling. That's the next thing on my checklist here. Downtime handling is this. We want to be able to do, let's just say we want to upgrade to the latest version of Flink, or we want to upgrade to some other piece of software on the cluster or whatever. And we want to, just real world stuff. We have this stateful computation going on, right? It's in the middle of computing. You might be computing hourly aggregates. You've got all this state in flight. We want to be able to somehow upgrade the cluster and maybe even move this computation to a different cluster, but nonetheless, not lose any of our state. And we just wanted this all to be as if we didn't take that action. So I'm going to that's kind of the motivation for this feature called save points. I'm listing all the current jobs, and I'm going to say Flink, save point, this. Okay? So what that is what we just did is this is built on top of Flink's normal fault tolerance mechanism. But it's a little bit different in that I initiate this save point. A save point is essentially a snapshot of all of the state across all the machines, the kind of global state of the whole computation. That's really the best way to think about it. All of the state, there's a point-in-time snapshot of all of the state in this whole computation. And once I have this, I can actually return to it at any given time and just continue computing from there. So I haven't interrupted anything. Life goes on. We're in this particular state. We're catching up. We're still kind of computing in real time. Let's just say from here, now that we have the save point, forget about killing one thing. I'm just going to get rid of the whole Flink cluster. Right? So we don't even have a Flink cluster right now. Of course, we're not going to see any data coming in. There's no processing happening. There's no Flink processes running anywhere. This is just going to say, hey, there's no Flink cluster. And so now we say we're going to upgrade the cluster, maybe even upgrade operating systems, or we want to move the computation to a different cluster, new version of Flink, whatever. It could literally be a whole different cluster, say. So what I'm going to start a new cluster up, and then I'm going to run my job again, but I'm going to say resume from save point. Oops. There. I'm going to run the same code as before. Sorry about this. Why is that there? And what I hope to see is that we pick up this computation exactly where we were, and there's not even not even a tiny anomaly. Everything should be exactly correct still. The sums should all be right, everything should all be right, everything should be in the same state. It should just continue like nothing ever happened. So let's see what happens. There we go. So that is what save points is. That allowed us to take a global snapshot of everything. Some period of time there's no cluster. We could have literally moved the computation to a different cluster, did whatever we want, and so we have these global consistent points. The next thing you realize you can do with these is basically reprocessing. So what is reprocessing? This is just another real-world production issue where, like, I want to change my code, or I have discovered some bug in our code and the analytics we've been computing for the last 6 months are wrong. So I just want to change my code and go and reprocess all the data, and yeah, just kind of recompute everything. So the tough part is it's a stateful computation, so there's nowhere in this data set is there a place you can go back to, unless you went to the beginning of all time. There was never a zero state anywhere along the way. But with save points, we can actually go back to previous points in time, into that exact state, even with all of these windows and everything else in flight. We can go back to that exact state with changed code and reprocess from there. So we're marking not only a place in the stream with a save point, but all of the state that was relevant at that point in the stream. So this is a consistent way to do this. The state is consistent with the input stream. So now, I'm just going to do, as an example of a code change, I'm going to jump in here. I'm just going to change, this is just one parameter, I'm just changing the period of all the waveforms. And then I'm going to rerun this code from my save point and see what happens. This just represents any code change. Okay, so let's compile that. And then let's shut down this guy. Now we already have a save point, so I don't need to make another one. I'm just going to use the one we already have. That's going to mark, this is where we want to start recomputing again. So I'm going to cancel the currently running job. I'm going to zoom out a bit further here so we can just see more data. And then I'm going to, should be nothing running. I'm going to run from save point again with the new code. There we go. So we literally, I'd have to back up even further so you can see. It took longer than I thought. Okay, so what we did is we reached back in time to some previous state of the system and some previous point in the stream, and we recomputed everything from there in a consistent way. This location right here is obviously where we took that save point, right? Now the thing you can do is this making and keeping around save points is completely up to you as the user. So you can make them periodically, so you can always go back to given points of time. You can make them just before you're going to shut down, so you can go back to where you were. You can actually have a branching idea. You can actually do A/B testing. You can have make a save point. You can have sort of the old version of your code still running in real time, and you can launch a second version of your code with a change. from the exact same consistent point. So now you kind of have like a branch, and you can do A/B testing, and you can compare the two. And then from there, you could branch again and again. So you can think of it as like, you can actually build something like, you can think of it like Git for the whole distributed application. Like you can have versions of things and like actually move back the different versions. It's actually pretty cool. Like I don't think we've thought through all of the things you can do with this, but the thing that's really important is you have a way to have consistent views of the application and do things like upgrades, et cetera, and still resume this like 24/7 type computation. Without something like this in production, you really end up into all kinds of problems. And these are kind of the new problems of stateful stream processing that need to be solved. So I think in Flink, we have a pretty good solution for these things. All right, so what else? I think we kind of got through it. That was data reprocessing. And yeah, Data Artisans is hiring. If you think Flink's cool or you want to work on this stuff, we are hiring. And we'd love to have more people involved. And from there, I don't know how we're doing with time, but I could take some questions. I think we're bleeding into the break now, but if anyone has any questions, I'm more than happy to take some. Yep. Yep. Yeah, that's a very good question. So he's asking, I'll just repeat the question. So if you have this stateful, you have this data flow, and all these operators have state, and you make a save point, and then you change in some fundamental way the actual computation you're doing, what happens, right? So basically the answer is that's up to the user. You can actually still, if you reuse some operators from the previous version of your code, they can still load the state that they had in the save point. If other things are just totally different, there is no state to bootstrap. So you have to think through, but these are the challenges of stateful stream processing, right? And any stateful applications. You have to think through what's going to happen to the state as we go forward in time. The other thing is, like, what if the state that you're storing, what if you want to change formats or something like that in the future? How do you make sure it's backward compatible and things like that? You can do all of these things, but some of that is put onto the user to do it right.
I think I missed a really basic concept.
Okay.
I'm associating streams with incoming real-time data or near real-time data.
Mm-hmm.
You do your save point, you have your shutdown or your intermittent loss.
Yep.
Bring it back up.
Oops.
All that data in the meantime just gone, or are you reaching back and grabbing all that?
Yeah. Right. So it depends on in a sense, it depends on your data source being stateful as well. And the way that typically this stuff works is your source operator is reading from Kafka, say, right? And the state of that operator is simply the Kafka offset. So when it comes back up in some previous state, the state from your save point, the offset, its state is the offset, that's where it ends up starting to read from Kafka again, and then everything goes forward. So it's sort of, for the model to really work, you need a stateful or replayable source fundamentally at some level.
You also need a computation that can keep up or go faster than real time, right? You can eventually get back to timeout.
Yeah, that's true, for sure, yeah. And so currently it's not there, but in Flink 1.2, you also have dynamic scaling. So it can automatically scale out and recover, and then back to real time, and then scale back down. That's coming. It's not there today. Another question?
So how do you correlate outputs to downstream data sources?
Outputs to downstream data sources. And what happens in the case of failure? Yep. Yeah. So another really good point. So in the case that we're demonstrating here, we're like computing aggregates and stuff, which ends up being, if you have to recompute that same aggregate, if there's a failure case, you're going to recompute the aggregate exactly like you did the first time, but the downstream system could potentially see two writes. So this real exactly once end-to-end is essentially not possible. What you can do is you can use state in the stream processor. Well, I mean, it's not impossible, but you have to do a lot of stuff. You can use state in the stream processor to do things that wouldn't have been idempotent in the past. You can sort of do the computation in the stream processor, which does have fault tolerant and managed state, and make sure that if you write again, just think of something simple like counting. Without like state in the stream processor, with that you can actually make sure that the aggregates, if they are recomputed, they're computed exactly the same the second time. But you still have issues with downstream systems seeing more than one message, so you still strive to make those writes idempotent. The other thing you can do is you can build exactly one sinks. Are we out of time? Yeah. So you can build exactly one sinks for certain data stores. Writing to Kafka is going to be a problem, but like if you're just doing like upserts in a database, you can do that, and you can also like with a combination of a sink and using Flink state as a write-ahead log, you can actually get exactly ones to the database too. But it's a little bit tricky. It is possible, but it's a little bit tricky. I think we have to wrap it up. I can maybe take one more. Anyway, go ahead.
How do you compare Spark streaming Apache Storm with Flink?
Yeah, he said, how do you compare Spark streaming and Storm with Flink? That's a great question. I actually worked on Heron at Twitter, so that's basically Storm re-implemented, so I have some experience there. Basically, everything I showed today doesn't really apply to Storm because it's not a stateful stream processor. You can't do any of these things, right? So I think that's just kind of like a previous generation. With regard to Spark streaming, it's just basically the architecture is just fundamentally totally different. Flink is actually a streaming data flow system, so data literally streams through these distributed processes. Whereas, and it gives you these nice properties with this continuous computation model and things like this, and it makes it very easy to do this kind of stuff correctly. And the architecture itself, we could get into, like there's lots of differences, whereas Spark streaming is still really a batch processor, right? Small batches, but it's still a batch processor.
Doing micro-batching or
In Flink?
inside is also doing
No,
micro-batching?
it's not. I think from there, we have to wrap it up, but I'll be happy to talk more afterwards. Thanks.